Hello, everyone. So, class begins. Today, we'll discuss the derivative and long-run multipliers for solving optimization questions. So, before we start our class, we have to learn the basic rules and functions of these two mathematical methods. Okay.
So, what is derivative? In mathematics, the derivative is a way to represent rate of changes. That is, the amount by which a function is changing at one given point. For functions that act on real numbers, it is slope of a tangent line at a point on the graph. The derivative is often written using dy over dx, meaning the differences in y divided by differences in x. A function's derivative can be used to search for the maximums and minimums of the function by searching for places where the slope is 0. So there are some trick rules of the derivative, and next slide are abstract of derivatives product rule and quotient rules. On the other hand, the second derivative is the derivative of a function depending on the result of the first derivative. When the second derivative is less than 0, it means the point is a local maximum point. When the second derivative is greater than 0, so the stationary point is local minimum point. But when the second derivative is equal to 0, it means we could have a point of inflection. In mathematical optimization, the method of long-run multipliers is the method of finding the local maximum and minimum of a function subject to equality constraints. One of the most common problems in calculus is that of finding maximum minimum of a function, but it is often difficult to find closer form of the function being string. Such difficulties often arise when one wishes to maximize or minimize a function subject to fixed outside equality constraints. The method of long-run multipliers is a powerful tool of finding this class of problems without need to solve the conditions and use them to eliminate extra variables.
Now, we're facing a tough architecture situations. We have an area of 200 square meters, but we want to build a lawn inside of this. We want to build another case surrounded by this lawn, which gives us the 2 meters on top and bottom, and 1 meters on the left and right side. On the other hand, we want to maximize the area of this green. So, what dimensions should give us the largest area?
Okay, firstly, I show our data on our mathematical models. This is the height, this is the width. We subtract 1 at left and right side. We subtract 2 at top and bottom side. And our green area is height minus 4 times width minus 2. Our question is what dimension will give us the largest green area. So step 1, we write a function for the item to be optimized. The space of green area is height minus 4 times width minus 2. Step 2 is to write constant equation as needed to relate to the variables will be used for substitution into the optimization function. Showing the background, the total area is 200. Width means height times width is 200. Width also means height is equal to 200 divided by width. We substitute width into the function we got before. The space of green area is 200 divided by width minus 4 times width minus 2. Step 3. Using the first derivative critical values and analyze to find appropriate relative max. Firstly, we let fx equal to 200 divided by width minus 4 times width minus 2. And then we can get first derivative function, which is 400 divided by width to the power of 2 minus 4. Because first derivative equal to 0, so we can get width value because width must be positive, we reject negative 10. We substitute width into our constraint function, we can get height is equal to 20. And now we substitute width and height into the function we got before. we can get that the largest green area can be 128 centimeters.
I have a solution too. I want to use Lagrange multiplier technique to solve this question. There are critical 3 steps to solve it. Step 1. Introduce a new variable lambda and define a new function f. As shown in the question, we can get 2 functions. The function 1 is fhw equals to h minus 4 times w minus 2. The question 2 is equals to wh equals 200. Let GHW equals HW minus 200. So we can get capital F WH lambda equals to FHW minus lambda times GHW equals to H minus 4 times W minus 2 minus lambda times HW minus 200. Step 2. Write the partial derivative equations that need to be solved for this question. So, the partial derivative represents h first is equal to w minus 2 minus lambda h. The third partial derivative represents w is equal to h minus 4 minus lambda h. Thirdly, the partial derivative represents lambda is equal to minus hw minus 200. Let the 3 partial derivative equals to 0, so we can get 3 equations. Step 3. Simplify the 3 equations to give the maximum dimension of green area. From equation 1, we can get lambda equals to w minus 2 over w. From equation 2, we can get lambda equals to h minus 4 over h. So, let equation 1 equals to equation 2. So we can get h equals to w. We let h equals to w be equation 4. Next, we substitute equation 4 into equation 3, so we can get 2w squared equals to 200. So we can get w equals to positive 10 or negative 10, because w is greater than 0, so w is equal to 10 meters and h is equal to 20 meters. Because fwh is equal to h minus 4 times w minus 2, so f maximum wh is equal to f 10, 20. So the maximum dimension of green area is equal to 128 square meters.